Okay, so this is section 3.8, and this is collision theory, and this is where we're going to talk about why reactions happen at the speed that they happen and what kinds of things impact that speed. So if you ask what's the difference between baking a cake at 250 versus 350, well, it's going to be obvious that the cake at 350 is going to cook faster. So just like baking cakes, reactions also, the rates increase with increasing temperature. Almost always. There are some minor exceptions that we're not going to discuss. Okay. So we've talked about the rate constant, and that the rate constant will stay the same even if I change the concentration of a reactant, as long as, and we've said, as long as the temperature is constant. But as soon as I change the temperature, I also change the rate constant. So let's take a look at why. So collision theory helps us understand what's happening at the molecular level that causes the rate to increase. So the first thing we need to know is that in order for a reaction to occur, we can't just have molecules on the opposite sides of a container. They have to actually not just touch, but collide. They have to collide with each other in order to react, because that collision is what results in the breaking of bonds, which is the first step in creating a new product. So rate increases with the number of collisions. So all those things that increase the number of collisions are going to also increase the rate. So let's first talk about concentration. If I have something that is a 1 molar solution and I change it to a 2 molar solution when I add something to it in order for it to react, what impact will that have on concentration? Well, as you can imagine, if I start with, let's say, this concentration and I increase it, even though my other reactant hasn't changed concentration, I'm going to increase the potential number of collisions that can occur between those molecules. And it doesn't really matter whether I change reactant 1 or reactant 2, right? It's also going to increase. But if I increase both of them, then I'm also going to increase further the number of collisions. So the higher concentration I have of my reactant or reactants, the greater the number of possible collisions, and therefore the rate is going to increase. So remember, we must have a collision in order to have a reaction. So if I have particles and they are colliding, why don't I have reactions all occurring instantaneously, right? Because particles are moving fast and they're likely to come in contact with each other, but why don't they all the reactions just go instantly if that's the case? So why does it take minutes or hours or even days for the reactions to occur? Well, that's because the collisions must have enough kinetic energy to break the bonds. If they don't have enough energy to break the bonds, they are simply going to bounce off each other. So it's all about having enough kinetic energy to break those bonds. And that's where we come into the idea of activation energy. The activation energy is the minimum amount of energy required to initiate or start a chemical reaction. And if that activation energy threshold is not met, the reaction will not begin. So these are potential energy diagrams. And on the left, you have an exothermic reaction, and on the right, you have an endothermic reaction. So let's take a look. We have mentioned along the way that we have this term delta H, which is the enthalpy, which has to do with the energy of a reaction. And the delta H is basically the difference between the products and the reactants. Okay? So if I look on the left, this is my delta H, right? Now, because my products are at a lower point than my reactants, my delta H is going to be negative. And a negative delta H tells me I am exothermic. Okay? I have lower energy when I am done. Okay? As opposed to on the right, the delta H, remember, it's just the difference between products, reactants, and products. This will be my delta H. Okay, and now I have a higher product than I do reactant enthalpy. So this is going to be a positive delta H, and it's going to be an endothermic process. Now, if I take a look at this peak here in both graphs, that's what I call my activation energy. Which is abbreviated as E sub A. And this you can consider to be the mountain that those reactants have to climb in order to begin that reaction. They have to have enough energy to start the process of breaking bonds, and if they don't achieve that much energy, they will not move forward and create products. You know, if they only get this much energy, then there's not enough to break the bonds. And if they get enough to break the bonds, you know, they could slip back left and go and reform reactants, or they could go to the right and form products. Okay, so they have to get over that mountain in order for that reaction to occur. And we can look at the energy activation barrier. You know, if you look at the exothermic reaction here, the activation energy is smaller than it is on the right, this endothermic process, where it's a much higher activation energy to get that reaction started. Okay. So at the top of the peaks, where I hit my activation energy, I have what's known as an activated complex. And this is a temporary state, and you could think of it as the jumbled mess associated with the bond breaking. And I have to have this activated complex. I have to reach this activated complex for that reaction to go over the energy activation barrier. And when I'm up there, when I have that activated complex, I can go back left and reform reactants, or go right and form products. Okay. So why does speed increase the rate? It's not as simple as having more collisions. This is what's going on. This graph here is known as both these graphs are Maxwell-Boltzmann distribution. And you need to be familiar with the Maxwell-Boltzmann graphs. And what they plot is the speed and the number of particles at each speed. Okay? So, in these graphs, A, the temperature is less than it is at temperature 2. Okay? We have this area under the graph for both, for those of you that know calculus, is the same, right? Because I have the same number of molecules. It's just when I have a higher temperature, I have a more flattened distribution. So here's the thing. If you think about kinetic energy, which is what the molecules need to reach that activated complex, it's 1/2 m speed squared, right? We'll just put the line over the mu to indicate that it's the average speed. So as I raise the temperature, I am increasing this. So with a higher speed, what I can look at is this green area. So let's say in T1, this little green shaded area represents the percent of the particles, let's say, required to break the energy of activation barrier. Okay? And if I increase the speed, what happens is I have a greater number of molecules or particles that are able to overcome the energy of activation barrier. So that's what speed does. I end up with a greater number of particles that are able to break the activation energy barrier. Okay, so we're going to stop right there and talk a little bit in the next podcast about all the factors and summarize.